Hi, everyone. Welcome to the first of two press conferences at this year's 56th annual meeting of the Division for Planetary Sciences, one of the divisions of the American Astronomical Society, or AAS. This is the first of two press conferences, and we have three excellent presentations from you to talk to you about today. Before we get started, I'll give you a brief rundown of how this is going to work. For those of you watching live, on the Zoom call, you can put your questions in the little Q&A box. And once we are done, we will have all three presentations in order. I will read them out loud for the benefit of those watching later, such that, each person can answer a question in order, and we have each person answer about the same number of questions. Each of the presentations will be about 10 to 12 minutes long, and we've grouped them by topic. So the ones today will be a little different than the ones on Wednesday. And two other things I'd like to note explicitly as I'm pulling up my notes is that, these speakers that you're going to be hearing from today, they've taken time out of their busy week at this conference to not network, not talk to their friends, not go get lunch with a new collaborator, but instead talk to you about the exciting work they're doing. This is something that takes significant time from them, and I hope that you can appreciate the hard work they've put into thinking and developing the talk you're about to hear. Please treat all the speakers and their topics with respect, regardless of their career stage, what kind of institution they come from, anything like that. They're doing this work for free for you, and it's a benefit to the community and the public. Secondly, we'd also like to say that these topics, like all the topics of the DPS, are of approximately equal importance, right? The DPS is a big tent. People do lots of work around here and lots of really interesting work. So as a result, I'd hope that you can, recognize just how much cool planetary science there is going on. In order to run today's meeting, we're running it with the help of some of the excellent staff of the AAS, including Dr. Susanna Kohler, Dr. Carrie Hensley, and newly Lexi Galt as well. It takes a lot of work behind the scenes to get these press conferences to run as smoothly as they do. Obviously, we're all wearing the blue screens, but there's all the stuff that goes into organizing them. It takes a lot of work, and it takes a lot of people to make sure that you can get all the stuff you do out of these press conferences. Our three presenters today are Quanzhi, who's going to be going first, Elizabeth Silber, who's going second, and Victor Oyiboka, who's going third. Their topics are all related to things about the inner solar system, the terrestrial planets, planetary defense, and comets and asteroids, right? And this means that some of the questions you might have that you should be putting in the Q&A box might touch on, aspects of each of their stories, each of their topics. And I'd hope that, we can come away from this all knowing more and getting more excited about the cool work that's getting done at this and also every DPS meeting. So with that, I'm going to hand it over to Quanzhi. I'm going to mute myself, turn off my audio, and then I'll point at you.
Okay. Can you hear me okay? Yes, everybody hear me okay?
Yes, we can.
Okay, great. Let me move that around. Okay. Yeah, thanks so much, Teddy, and thank you all for being here. I'm Quanzhi. I'm at University of Maryland, Boston University. And today, I'm going to tell you about the work that we did on potentially hazardous asteroids in the Taurid resonant swarm. I give this presentation on behalf of my awesome collaborators, especially my student Jasmine Lee, who actually did the bulk of this work, but unfortunately couldn't be here because she just started her college. So shout out to Jasmine. It's about the Taurid resonant swarm. So I guess I will start with a quick introduction of what Taurid is. Taurid, the Taurid meteor stream or meteor shower, it's a major annual meteor shower that is active in approximately June and November each year. It is the dust debris shed off by a comet known as the Encke's comet of 2P Encke. And the Taurid meteor stream is part of a large interplanetary complex system that comprises of the Encke's comet, the Taurid meteor shower, and also possibly a number of asteroids. It's believed that the Taurid complex is originated from a large breakup event from the progenitors of Comet Encke, possibly from a large breakup event that happened very recently by astronomical timescale. That's about 10 to 20 thousand years ago. And this progenitor, the size of this progenitor is debated, but some believe that it could be as large as about 100-kilometer class. So it's very large. On the left-hand side here, I'm showing the Oh, another interesting thing about the Taurid meteor shower is that even though the activity level is not particularly high, something like the Perseids and Germinate meteor shower that you might have heard of, but it's particularly rich in larger particles that's good in producing fireballs or very bright meteors. On the left-hand side here, I'm showing a composite image taken by the NASA Fireball Network that shows some of the Taurid fireballs. And the Taurid meteor shower has been known for more than a century. We have very good data of it. And one interesting thing about the Taurid meteor shower is that apparently there is a year-to-year variation of the activity level. On the left-hand side here, I'm showing a figure by Dubitis and Alt, published in 2007. This shows the level of activity of the Taurid meteor shower with respect to time, and you can see that there are years that the activity level is higher than other years. And combined with dynamical studies of the Taurid meteor stream, we come to realize that there is Jupiter actually play around with the Taurid meteor stream. Jupiter play around with many things, including the Taurid meteor stream. And Jupiter's gravity effectively protects a part of the Taurid meteor stream from dissipation. And these spots are known as the mean motion resonances. And therefore, in these spots, the flux, the density of the Taurid meteors is higher than other places. That means in certain years, when the Earth passes close to the center of such mean motion resonances or swarm, we see an enhancement in the meteor flux, and as shown on the figure on the left-hand side. And this is particularly interesting because if they contains a large number of larger particles, they could also contains larger objects such as asteroids. Some of them could be pretty big and could be potentially hazardous. And over the recent years, near-Earth object surveys have found several 100-meter class asteroids that may be associated with this one. So it's kind of both interesting and to some extent worrisome, because as the Taurid meteors, such asteroids will also cross Earth's orbit, meaning that they could one day have impacted Earth. So a question then becomes, how many potentially hazardous asteroids or PHAs are in the Taurid swarm? Because we don't we know that near-Earth asteroids are kind of like randomly distributed in the solar system, but the Taurid swarm is kind of more coherent, and they follow a certain path. And that means if they could come in a certain direction at a certain time. And so we want to know whether we could be facing the so-called coherent impact from such bodies. The nice thing about the Taurid swarm is, as opposed to near-Earth asteroids, which I just mentioned is randomly distributed, they follow a certain path in the planetary space, meaning that you could look at the models and see when will they pass close to the center of the swarm. So David Asher has published this table showing what are the good years to observe the swarm. Showing here are the angular distances to the center of the swarm. I recognize the unit is kind of weird, but basically, if you have a delta M close to 0 degrees, that means the Earth is closer to the center of the swarm, and anything that's between minus 40 to plus 40 degrees are kind of like a good year. So you can see that the best encounters in the past several decades are 2019, where the Earth is passed only 5 degrees off the center of the swarm. My colleague Dave Clark and his collaborators, or co-authors of this work, attempt to use the Canada, France, Hawaii telescope at Mauna Kea to try to look for to try to search asteroids using this opportunity, but they had issues with the weather in technical issues, so they couldn't get data. The next best opportunities after 2019 is actually 2012. It's not as good as 2019, but still kind of quite good. So we secured some time on the Zwicky Transcend facility. And the Zwicky Transcend facility, or ZDF, is ongoing survey project making use of the 1.2-meter telescopes in Palomar Observatory in California to survey the entire visible northern sky. And the really cool thing about ZDF is that it has a dedicated wide field camera that is the largest camera on any meter class telescopes. It can cover 47 square degrees in one shot, cover an area that's equals to 235 full moons. So it's very large in terms of sky coverage. So it's ideal for the work that we plan to do. We conduct two passes of observations on October 29th and October 31st, the time that the Earth passed closest to the center of the swarm. And here in the figures, I show you the footprints of our survey. All these blue dots are the simulated the on-sky positions of simulated 100-meter class swarm asteroids. The figure as a plot is a little deceiving, but we can actually cover about 99% of all this 100-meter class simulated swarm asteroids, so it should be pretty complete. We have a suite of asteroid detection software running with ZDF that will look for things that are both point source-like or smeared, as happens with asteroids that pass very closely Earth. Long story short, we didn't find any Taurid swarm asteroids, which may seem a little bit discouraging in the first place, but the nice thing about non-detection is that you can use it to derive useful upper limits. I will save all the mathematical details here, but long story short, we conclude that there are no more than 9 to 14 asteroids of 100-meter class or bigger within the swarm. Quick takeaway from that is that there are not that many PHAs in the swarm. And as a reference, there are approximately 3,000 PHAs that have been found, and model predicted that they may be as much as about 5,000 PHAs in the inner solar system. So an upper limit of about 10 PHAs is quite modest. So it's a good news. There's not that many PHAs hiding in the swarm, and we can also use this upper limit to place a constraint on the progenitors that create the Taurid swarm, the Taurid complex. We conclude that is likely to be near about 10 kilometers in class, which is not as large as previously hypothesized. With that, I will stop here. Thank you very much for your attention, and I hope that our work can make you sleep a little bit better, knowing that there's not that many dangerous asteroids hiding in a certain spot in the sky. Thank you. The wrong button, sorry.
Only at a planetary science conference would someone sound disappointed when they didn't find a dangerous asteroid. Next up, instead of talking about asteroids related to meteor showers, she's going to be talking about the actual meteors and bolides and fireballs themselves. Is Elizabeth Silber from Sandia National Laboratory. I'll mention one last time as she's getting set up that if you have questions for any of these attendees, please put them in the Q&A box on the Zoom chat, just so they're all grouped together and I can read them after they're done. But with that, I'll say, Elizabeth, the floor is yours.
I hope you can see my presentation. Before I start, I'd like to give a shout out to my co-authors who are my interns. Two of them were my summer interns, and they're back to school, and two remain as my year-round interns. Can you see my presentation advancing? I guess you can't.
No.
It seems to be. There we go. Our planet is continuously bombarded by particles from outer space. In fact, about 25 million particles enter daily. Most of these are super tiny and burn up very high up in the atmosphere. Rocky, icy, metallic fragments up to 1 meter across are called meteoroids. These objects could be as small as dust and grains of sand and as large as an SUV tire. After entering the atmosphere, these objects heat up and interact with air molecules to produce a luminous path called a meteor, or what we frequently refer to as a shooting star. Very bright meteors are called fireballs and bolides. Asteroids are larger than 1 meter across. And as I mentioned, most objects vaporize high up in the atmosphere before ever reaching the surface. However, asteroids and large meteoroids generate shock waves, which sometimes can be felt on the ground. The good news is that large objects are not as frequent as small stuff. The bad news is that large objects can be much more destructive. The most recent example is the Chelyabinsk event. On February 15, 2013, the city of Chelyabinsk, Russia, experienced a powerful asteroid explosion that impacted the area with a force equivalent to 440 kilotons of TNT, which is about 30 times more powerful than the Hiroshima bomb. This was an extraordinary event caused by 18 meters wide asteroid approaching from the direction of the sun, which made it nearly impossible to detect before it impacted. It resulted in widespread destruction, including thousands of broken windows, as we can see on the photo here, and numerous injuries. The asteroid's shallow entry angle, and we can see the path, the smoke path in the upper photo. Shallow angle intensified its impact, making it one of the most significant bolide events in recent history. It was witnessed by many, recorded by various instruments, from ground sensors to satellites, and it serves as a reminder of the potential threats posed by near-Earth objects. Efforts to advance our understanding of asteroids utilize a range of observational methods. These include space-based sensors from US government and ground-based sensors like all-sky cameras, radar, eyewitness reports. There is no single method that can provide all of the answers, so we need to use a combination of these approaches to create a more comprehensive understanding of asteroid events. Notably, infrasound is an essential sensing modality due to its global coverage and ability to estimate impact energy, making it invaluable for assessing potential threats. Despite advancements in observational techniques, many questions still remain unanswered, highlighting the critical need to leverage all available strategies, especially infrasound, to better characterize impacts. Infrasound is low-frequency sound below the range of human hearing, typically below 20 hertz. Infrasound sensing plays a crucial role in detecting asteroid impacts by capturing low-frequency sound waves generated by these events. It has an ability to travel long distances, which allows for vital information on the timing and location of impacts. So by measuring infrasound signals, specifically signal period and amplitude, we can estimate the energy of an asteroid, which is essential for assessing potential threats to Earth. In addition, infrasound data can complement other observational methods, such as cameras, to create a more complete understanding. What is making infrasound very useful is the fact that infrasound sensors can be deployed in remote or hard-to-reach areas, and they function effectively in all weather conditions and provide continuous global monitoring when it comes to bolide activity. So understanding energy deposition from asteroid impacts is imperative for assessing potential threats to Earth. Traditionally, energy estimates rely on space-based observations of light flashes, with about 1,000 events cataloged on the NASA JPL CNEOS webpage since 1988. While these data provide valuable information, such as ground truth, in some cases velocity and altitude of peak brightness, many more bolide events remain unreported, which underlies the need for more robust energy estimation methods. And one approach uses infrasound signals, and as I mentioned, specifically signal period or amplitude, to estimate impact energy. However, challenges arise because existing empirical energy relations were primarily developed for different types of explosions and for stationary sources. So given inherent variability in asteroid entry characteristics, a comprehensive strategy that integrates various parameters extracted from infrasound data with parameters obtained through space-based observations is absolutely essential. So by considering large parameter space that comes from combining these methods, we hope to more accurately estimate energy deposition. So here is an example of two events. On the left is Chelyabinsk, and on the right is Indonesian bolide. This demonstrates different energy relations relative to CNEOS energy. So this is just to demonstrate how estimates can vary significantly from different relations to a different relation. So we certainly need to find a more robust way to quantify impact energy. So in our work, we analyze a representative set of bolides as case studies to conduct a thorough investigation of their impact characteristics. So this involves comparative analysis of signal parameters, physical attributes, and light curves to differentiate between fragmentation and airburst events and cylindrical line source because their shock geometries vary significantly. Furthermore, we explore the fidelity and reliability of energy estimates derived from infrasound, and compare these estimates with values published on NASA CNEOS database. So our ultimate goal is to develop a practical and comprehensive approach for estimating energy associated with asteroid events. And we integrate findings from acoustic data with established observational methods. And with doing that, we aim to advance our capability to assess potential threats. And that will help us improve our preparedness for future asteroid impacts. So understanding the influx rates of objects ranging from meters to tens of meters in size is crucial for planetary defense. These objects are very faint and difficult to detect telescopically. They're least quantified in our neighborhood, and they can improve our ability to divine frequency of potential impacts. Our goal is not to only leverage infrasound to estimate impact energy, but also evaluate risks associated with different size classes of asteroids. And this capability is critical with monitoring for monitoring potential threats, particularly in areas where other instruments have limited coverage, ultimately leading to improved risk assessment. In my concluding remarks, I emphasize that detailed studies utilizing multimodal detections of fireballs can provide valuable information for model validation and refinement, especially in events where ground truth data are sparse. While energy relations that rely on signal period are generally very useful, it is essential to consider how incorporating other parameters, such as physical properties of bolides, along infrasound characteristics can improve and refine comprehensive analysis. And in conclusion, this holistic approach is crucial for advancing planetary defense strategies and for improving our ability to estimate energy yield when relying solely on infrasound data, and staying tuned for publication. That's it for me.
Well, thank you so much, Elizabeth. You know, we're not going to be able to know everything we want to know about the asteroid that will, put us in some danger someday. But learning all the different things we can on the way there is a critical part of staying safe and making sure that we can be as prepared as we can. With that, I'd like to welcome our third speaker, Victor Oyiboka, to get ready to share his screen. We've talked about asteroids out in space that might cause us some danger. We've now talked about things burning up in the atmosphere. So the only natural place to end here is talking about the ground. Victor will be talking about the formation of the terrestrial planets. Whenever he's ready. Okay, I'll mute myself and turn off my video. Victor, the floor is yours.
Yeah, can you see my screen?
Yep, looks good.
Hi everyone, good afternoon. So my name is Victor Oyiboka, and I'll be talking about the role of radioisotopes in the formation and evolution of terrestrial planets. First of all, I'm also an incoming PhD student of University of Texas at Dallas, and you can reach me on Twitter at Planetary Victor. My collaborators are Farouk Akorede and Busari Moruf. Farouk Akorede is from University of New Mexico, the first year PhD student, while Busari Moruf is a first year PhD student at the University of Idaho. Sorry.
If you need to just share your PowerPoint too, that's cool.
Yeah, okay, yes. So first of all, we need to know what are radioisotopes. So radioisotopes are radioactive elements of radioactive isotopes of an element, and they are also described as atoms with extra energy in their nucleus, or an unstable mixture of protons and neutrons. So we have the number of protons in the atomic nuclei of different isotopes, which have the same elements, and also the number of neutrons varies. So we have different radioisotopes, we have for thorium, we have for uranium, we have for polonium, different metals have different radioisotopes. So we are looking at short-lived radioisotopes and long-lived radioisotopes. So although the short-lived radioisotopes, which were used to form planets, are all extinct, which are the radioisotopes of aluminum and iron, that is the radioisotope of 26 aluminum and the radioisotope of iron, while we have the long-lived radioisotopes, which are the radioisotope of potassium, 40 potassium, the radioisotope of 232 thorium, the radioisotope of 235 uranium, and the radioisotopes of 238 uranium, which are all still in existence. So although the radioisotope of aluminum and iron, they were important sources of heat and important sources for the formation of planets, but now they are all extinct. So when we look at the radioisotope of aluminum, aluminum was probably the most important heat source during the early formation stages of planets, but now it's extinct in planetary bodies. It decays with a half-life of approximately 717 kiloyear into the stable 26 magnesium, and it also decays with the beta decay with a probability of 0.8173, although we are not looking onto that. Also, when we talk about the radioisotope of iron, it also have an half-life of 2.62 milliyear, which translates to 2 beta decays of cobalt and nickel, and also is extinct in planetary bodies. We are looking at the radioisotope of potassium right now. So we have that potassium is the most abundant among the 4 long-lived radioisotopes. It also contributes most of the radiogenic heat of the core. The decay branches are the decays of beta, and also which is directly to the ground state of calcium, and the decay branches also have the positive beta decay, which produces argon by electron capture. So we have the process of decay here, which it decays to calcium, to the negative electron, and it also has to 1.31 million electron volts. Also, we have the radioisotope of thorium. The thorium is the radioisotope with the longest half-life among the four long-lived radioisotopes. It has 14, it's approximately 14 gigayear, and it is the only isotope of thorium that exists now in appreciable amount. It also has a long decay chain consisting of several alpha and beta decays. Sorry. From this. Yeah, so okay, yeah. So the long decay chain includes the decay of 212 bismuth, which has 2 decay branches. It also decay via the alpha decay, approximately with a probability of 0.3593 to 208 titanium, or via the negative beta branch, which approximately probability of 0.6407 to 212 polonium. Also, the final stable daughter of 202 thorium is 208 lead, and each decay of thorium eventually also produces 6 atoms of helium, 6 atoms of 4 helium. So this is the decay. This is how it decays from thorium, decays onto 208 lead to 4 helium, and also have 4 negative electron, and also 42.7 million electron volts. Next, we look at the radioisotope of 235 uranium, which is less abundant, and it is shorter lived. It also has a half-life of 7.4 milliyear compared to the isotopes of 230 uranium. It has a longer and complex decay chain compared to that of thorium. The decay chain includes the negative beta decays of 231 thorium, 227 actinium, 223 francium, 211 lead, and 207 titanium. And the final stable nuclei of uranium is 208 lead. Each decay also produces 7 atoms of helium. So first of all, we have for thorium, which produces 6 atoms of helium. Now we have a 235 uranium, which produces 7 atoms of helium. And this is how it decays. So next, we have the radioisotopes of 238 uranium, which is more abundant and has a higher half-life compared to that of 235 uranium. The half-life, and it also has a long and complex decay chain. The decay chain includes the negative beta decay of thorium, of polonium, of lead, of bismuth, titanium, and also the final stable daughter of 238 uranium is lead. So each decay of 238 uranium eventually also produces 8 atoms of helium. So now we realize that the radioisotopes of thorium, 235 uranium, and 238 uranium produces lead and also produces 6 atoms of helium, 7 atoms of helium, and 8 atoms of helium respectively. So next, we go on to the half-life. Half-life, we also want to know the definition of half-life. Half-life is the time required for 1/2 of the atomic nuclei of a radioactive sample to decay. So we have the half-life of each of the long-lived radioisotopes, which are here. So we have the half-life of potassium, which is 1.277 times 10⁻⁹ years. Then we have for thorium, which is 1.405. Then one for uranium 235, which is 7.038. The one for uranium 230, which is 4.467, which is the longest half-life. Then we also need to know the specific heat capacity. So the specific heat capacity of each of the radioisotopes. The specific heat capacity of a substance is the quantity of heat required to change the temperature of unit mass of a substance by 1 unit. So the specific capacity of potassium is 2.92 times 10⁻⁵ weight per kilogram. For thorium, is 2.64 times 10⁻⁵ weight per kilogram. For uranium is 5.69 times 10⁻⁴ weight per kilogram. And for 238 uranium, we have 9.46 times 10⁻⁵ weight per kilogram. Next, we go into the different stages of the planet formation, how the heat contributes to the different stages. So this figure, the first figure here, represents the initial heat productions of potassium, thorium, uranium 235, and uranium 238. So we have the starting heat production, which is by the left. Then we also have the time after galactic formation, which is calculated in gigayears. So this is the first figure above, and this total in cosmochemically Earth-like exoplanet mantle as a function of their formation time. So these are the different formation time. So we have for 5 gigayears, we have for 10 gigayears, we have for 15 gigayears, and we have for 20 gigayears. So we have different formation time for potassium, for thorium, for uranium-235, and for uranium-238. And this is the total Earth, which is here, which is this black dots here. Then next we go on to the second diagram. This figure here above indicates the heat production rate for the first 4.5 gigayears after exoplanets that formed 0 years, 4 years, 8 years, and also 12.5 gigayears into galactic history. So we have the heat production, which is calculated in 10⁻⁻12 weight per kilogram in mantle. So, and we also have the geologic time, so which is also 1 gigayear, 2 gigayear, 3 gigayear, and also 4 gigayear. So we have for the different radioisotopes. Now we go on to the next one. This figure above indicates the concentration of potassium, thorium, uranium-235, and also uranium-238 in exoplanets today, which is as a function of their age. So we have the concentration today, which is concentration measured in parts per billion. We have 50, we have 100, we have 150, and up until 450. Then the next, we have the planet age, that's which we have 12 gigayear, 10 gigayear, 8 gigayear, 6 gigayear, and up to 4 gigayear, up onto 2 gigayear. So we have them. Then for the different isotopes, for potassium, for thorium, for uranium 235, and for uranium 238, and which are indicated with these colors above. So we have the one for potassium, which went up until 450, and we have the one for 132 thorium, which went to 100 up until 130. We also have the one for 235 uranium, which is this color indicated here, and we also have the one for 238 uranium, which is this color indicated here. So this is it. And lastly, the figure above indicates the current heat production in exoplanets as a function of their age. So we have the heat production, which is measured in weight per kilogram, and also the planet age per gigayear. So we have for potassium, thorium, uranium 235, and uranium 238. And this is the total Earth, which is this black dot. So we have for the different radioisotopes here. So thank you. And lastly, we have the Ure ratio. The Ure ratio, which is defined as the ratio of internal heat production to surface heat flux. And also, the Ure ratio is divided into bulk Earth Ure ratio and the convective Ure ratio. So the bulk Earth Ure ratio is the ratio of the internal heat generation in the entire Earth to the total surface heat flux. The convective Ure ratio is the ratio of the internal heat generation in the mantle over the mantle heat flux. So we have the present day thermal budget. We have present day thermal budget, which is the global heat flux. For these are different values: 46 oceanic heat flux, 32 continental heat flux, 14. So we have the different heat flux. Yeah, thank you. This is my presentation. Thank you.
Okay, thank you, Victor. It sounded like someone was knocking at his door, so we'll get to him for questions third. But I wanted to say thanks to all of our presenters, and for all three of them, if you could turn your videos on, we have time for maybe 2 or 3 questions each. I'll mention 2 things just as we're getting set up. I know a lot of science journalists will be watching this later, and many of them will have traveled to Florida for the Europa Clipper launch. So I hope that given the weather condition down there, you're all staying safe and sound as much as you can be. There have been a lot of questions in the chat, and I want to say thanks to everyone who's asked them. I'm going to go to Quanzhi first. So again, I will mute myself, turn off the volume, do the whole song and dance. The question from Richard Lovett asks, is there anything you can say about the risks posed by potentially smaller asteroids in the Taurid swarm? For instance, in Elizabeth's talk, we talked about the danger posed by an 18-meter asteroid, but in the case of your talk, you were able to rule out, some of the really, really big, really, really dangerous ones, and how you might, be able to comment on what the Taurid stream is like at these smaller sizes.
Thank you. That's an excellent question. And actually, that's something that's now in our mind, since now we have the 100-meter class asteroids sort of ruled out. The tricky thing about the smaller asteroids is that they are much harder to find because they're fainter. And when they're bright enough, that means they're closer to the Earth. They will move much faster, and that will sometimes require a different surveying strategy, which our 2022 work is not really aiming into that direction. But the nice thing, if you remember the table that I show, is that there are a pair of actually quite good opportunities coming up in next year and the year after next, 2025, 2026. And another good news is that we just heard that the ZDF survey has been funded by NSF for another 2 years. So we are thinking of using the opportunities next year and then year after next year to do a more dedicated search with strategies better tweaked towards smaller asteroids. So hopefully we can say something more about those. But in short, I agree. Yeah, those are the things that you probably not worry about regional destruction. But as you have mentioned that like the Chelyabinsk event, they can still cause some localized damages if they happen to explode over a big city, for example. I hope that answers your question.
Great, thanks. So circling next up to Elizabeth, one of the questions that came up in the chat was, just how many objects have the kind of infrasound data you're looking at, and, maybe how it's actually helping you, compare to, assessments of planetary defense from other methods. Maybe it's asteroid surveys, maybe it's something else. You are on mute.
That is a fantastic question. Thank you for bringing that up. We have been focused on looking at specifically bolides listed in the CNEOS database, because the CNEOS database contain important ground truth information, in many cases also the altitude of peak brightness, as well as the velocity vector, which we can use to establish the entry angle and other parameters. My intern, Miro, has been working for the last couple of years developing a infrasound processing tool. He has actually paper ready and is going to be submitted to SRL, so stay tuned for that publication. That tool has capability to process large data sets all at once. And then we go and sift through all of the detections with a little bit higher precision. Nevertheless, we expect about 30 to 40% of all bolide events to be also detected by infrasound, which is much higher than previously expected and anticipated. We're able to see even smaller events. And that actually helps us a great deal, because satellite observations have global coverage, and infrasound can also provide global coverage where we actually don't have any other observational means, such as cameras. I mean, keep in mind that Earth's coverage is 75% of oceans. So infrasound can provide that crucial information about how big event was, and our goal is, in absence of any other observational technique, to be able to use infrasound to gather a little bit more information, which will actually fill in the gaps about these objects that are meters to tens of meters in size that can potentially pose threat.
Sweet, thank you. The next question is for Victor. I'm going to slightly paraphrase something in the chat and add a little bit of my own flair to it. In your talk, you talked about, how these long-lived radioisotopes provide, maybe an under-accounted for heat source for both the terrestrial planets, but also for potentially rocky exoplanets. I was wondering if you could talk about how, whether or not this extra heat might have, facilitated some of these planets being habitable, or at least, closer to habitable. I know it's always sort of hard to tell with exoplanets, but whether or not this might, open up the realm to, more planets being worthy of following up, or whether or not there's something more complicated going on.
Okay, yeah. So let me get a question. So do you mean that due to this radioisotopes formation, more planets are forming?
I guess my question is like, are any of them, does this make any of them warm enough to be a nicer place for life, or, the search for life, that kind of stuff?
Oh, yeah, yes, for sure. Yeah, so as the radioisotopes are forming, so different planets are being formed every day. So right now we have about almost 6,000 planets, different exoplanets formed. So they are still searching for more planets. We are in the search for more planets. And these radioisotopes are important heat source for these planets. I guess they are important heat source for this planet. So that is the role of the radioisotopes. So they generate heat, and also they help in the formation of the planets. So different form, they are formed in different ways. So if we have the different types of planet formation, we have the planet formation, we have the planetesimal formation, and we have the normal planet formation. So the radioisotopes are important heat source to the formation of this planet. Yes.
Okay, great. Yeah, I have a follow-up question, but I'll come back to you in a second. There was a question in the chat that sort of goes to both Quanzhi and Elizabeth, so I'll sort of frame it at both of you, and we have time for maybe one more question each, but we'll see how we can squeeze it out. One of the questions here is that you're both kind of going after asteroids that are potentially dangerous, either on the small scale or on the bigger scale. The question, that I might pose to both of you is how does the work you do actually affect the way that we're doing planetary defense in a day-to-day stuff? If you're someone who's planning for these kind of events, if you're trying to think about what people might do in what order, how does your work help people plan? How does it, actually, how does the rubber hit the road and make us all a little bit safer? And I'll say Quanzhi first, just so we can keep the round robin circle.
Right. That's a very interesting, very good question. So it's kind of related to my work, but over the past decade or so, we really see the rise of ground-based and space-based near-Earth object NEO surveys. We start picking up imminent impactors that is telescope can actually see them just hours before they hit the Earth, and therefore places like the Minor Planet Center, the nerve of the international asteroid detections, and places like JPL can issue and ESA can issue asteroid impact warnings, so astronomers can get around the clock to try to observe and characterize asteroid while it's in space, and meteor scientists can start looking for the fireball and search for fragments if they land on the ground. And that's a lot of work has been devoted into making our asteroid detection softwares better and better. That's happening in every near-Earth object, telescopic near-Earth object surveys. For example, at ZTF, we have code, some machine learning assisted to look for things that are of strange shape. For example, asteroids are so close to Earth that they actually smear across the images, so we can identify them from the images. So in all, the idea is that we have better telescopes now. We have better computers, better software to find those asteroids before they hit the Earth. And I was hoping that there will be a day that we can issue out this asteroid impact alerts so that the people can either go out and see a big fireball in the sky, or at least, for example, something like Chernobyl event can warn people to stay away from windows, just so that the explosions of bolides, when windows are shattered, when the explosion hit the ground, that will keep people safe, because that's actually the #1 reason why the Chernobyl event that's causing so many injuries. It's not because they are hit by asteroid fragments, it's because they were right next to windows, so they are but they're injured by the shattered glasses. So yep, and I hope that answers your question. And maybe Elizabeth, you'll also have some comments.
Yeah, thank you. In adding to that, I would like to mention that from perspective of shockwave deposition and shockwave effects from bolides, what's important to understand, and we're interested in how that shock is distributed. As I mentioned, Chelyabinsk had a very low shallow angle, which basically meant it traversed a longer distance, depositing the shock energy down on the ground. Of course, if we have a more steep entry, then more energy is going to be more concentrated in a certain point. So it's not a win-win situation either way. So from that perspective, we want to understand the shock deposition. Also, if we have any events over remote areas, which are not covered by optical means or any other observational means other than infrasound, we want to be able to more robustly and reliably establish what the energy deposition is. And then from energy deposition, we can extrapolate potentially the size of the object, which can help us refine our flux estimates. And finally, I have collaborative work with my colleagues from UC Santa Barbara, Dr. Phil Lubin's group. They're working on disruption of asteroids. So if we have an imminent threat, not that's 20, 30 years away, but if we have disruption of an asteroid closer to Earth, if we have incoming fragments, we want to better understand how those fragments can actually affect the surface and chemistry of the atmosphere. So I will, in my kit, I will post some publications that have been recently published, and you feel free to reach out to me or to Dr. Lubin actually to discuss in more detail. Thank you.
Okay, cool. And the last question, at least for today's press conference, though I will remind all of you there is another, is for Victor again. One of the things you did in your work is you assumed that, these exoplanets, when they formed, they were forming with an Earth-like composition, right? They were forming with the same, relative abundances of uranium and thorium and all these other things as the Earth has. I was wondering how much we think that might vary from exoplanet to exoplanet. Are there going to be exoplanets that might form in a particular, environment, a particular part of the galaxy that might, say, for instance, follow a different track for which this heating is more or less important? You're on mute.
Okay, yeah. So I didn't get it clearly. Sorry.
It's all good. The question was more or less, you assumed for your exoplanets, for your simulations you were shown at the end of your talk, that they all had an Earth-like composition, an Earth-like, abundance of thorium and uranium and all that other stuff. Would you expect that to vary quite a bit for exoplanets? Are there going to be parts of the galaxy or kind of environments where, your work would, underestimate or overestimate the kind of additional heat these might provide?
Oh, yeah. So the heat varies. The heat varies. Like I said, the radioisotopes are each they are important in the formation of this planet. So the heating rate for each radioisotope varies for like different planets. So we have like the Earth-like planets, the Mars-like planets, the Venus-like planets, and they are all terrestrial planets. So the heat generation for each of the exoplanets, they vary. Are you getting me? So the heat generation for like Earth-like planets, they vary from the heat generation for the Venus-like planet, and also they vary for the heat generation for the Mars-like planet. So from there, we'll get used to more planets, get used to new and different exoplanets, which are being formed and evolved daily.
Okay, cool.
That's
Well, I'm going to take this as an opportunity to thank all three of our speakers again. They took time out of their conference to talk to you all about their science, and that's really cool. And that's an amazing opportunity. For those of you who are watching later, the AAS is going to post, information about each of their slides, about their presentations, about how you might contact them. And I'd really encourage you to do so, whether or not that's in a couple hours, a couple of days, or maybe a few weeks down the line when you realize there was a question you should have asked. I'll also say thanks again to the AAS folks, especially Dr. Susanna Kohler, for helping to organize all this stuff. It's a lot of work behind the scenes. The DPS is a meeting with a lot of stuff going on, so I don't want to run this too late because I'm sure our presenters have talks and sessions to get to. We have a plenary that I think starts in 15 minutes, but I will say one more time, thank you to all of you who are watching. Thank you to all of you who are watching later. I hope you're all staying safe if you're down in Florida. And as one last item, there's one more press conference coming up in 2 days, starting at the same time, 12:15 on Wednesday, with 3 more talks with a little bit more of a gas giant and exoplanet focus than what we talked about today, though of course we did talk about some of those things. And with that, I'll say thanks so much, and see you, most of you, hopefully even more of you, on Wednesday.